Alright, hello everyone, Simon here, and welcome back to the ARCHMINE100 series where we're learning architectural concepts through Minecraft. So the fourth lecture is going to be on color. If you're American, you would spell it without a U, but I'm not American, so color with a U. So, colors are pretty, they are. So for most people, our eyesight is what we use to sense the world. We use our sight most of all, uh, in comparison to our other senses like touch and sound and smell and taste. Like our eyesight is quite important to us, and unfortunately, some people are blind, and that is a severe handicap. I mean, they still live, hopefully, with enough help and suitably designed environments, let's say, then even blind people can live fairly comfortably. But without eyesight, we are severely handicapped. And so sight is very important. And when we see the world, most of us see the world in colors. Some of us are colorblind, so we're not completely blind, but some people can't see colors or they can't see certain colors. So some people, I think most common is blue-green colorblind, where people who are blue-green colorblind can't, have what they can, but they have difficulty telling the difference between green and blue. Or is it red-green colorblind? I think there's blue-green, there's red-green colorblind, where you can't tell the difference between red and green. And there's other types too, but in any case, like colorblind reduces people's ability to see colors. But most people in the world can see, and they can see full colors. And the colors are the result of the way our eyes and brain sense and interpret light. And that's important to keep in mind, and I'll explain pretty soon. In fact, I'll explain right now. So light, I mean, the way we see colors is not really how light is. Light, objectively, scientifically, light is electromagnetic radiation. And the visible light is only a very narrow spectrum. You see that little chart there on the left. The visible light is only a very narrow band that extends upwards to ultraviolet and X-rays and gamma rays, and then down to infrared and microwaves, radio and TV waves, and then longer wavelengths. So electromagnetic radiation is waves, but also photons and particles because of quantum physics. So they're photons and they're waves. So the wavelength is how how close together the each wave is, or how closely they oscillate. And the electromagnetic radiation that we can see is only a very narrow band between wavelengths of about 400 to 700 nanometers. Whereas they can go much higher than that to into kilometers in terms of wavelength, and then much narrower than that. So what we see is only a narrow band of the actual energy, electromagnetic energy out there. We see those colors because that's the electromagnetic radiation that is useful to us, because the Earth's atmosphere blocks out most of the radiation from the sun. But it does let this narrow band through very clearly, so we use this narrow band to see things around us. But that's not the only electromagnetic energy in the world. In fact, it's only a very small part of all the energy in the world. Some insects can see into the ultraviolet. I think some other animals can see more into the infrared. Infrared is basically heat, like you feel that as heat. But what I'm trying to say is, I'm not explaining the physics very well. I mean, I'm doing architecture, not really physics. But if you kind of understand the physics, what I'm trying to say is that our interpretation of light energy is really a very limited fraction of all the electromagnetic energy out there in the universe. So we see only a small part of what's really out there. And we see it through the eye. So this is like a top view of the eye, although the eye is spherical, so the side view is very similar. So at the top of that diagram there is the cornea, and then beneath that is the iris, and then the lens, and then the vitreous humor chamber. And then at the back of the eye, at the bottom, is the retina, and then the optic nerve. So the light comes in through the cornea, and it's focused through the lens. The lens projects the light that comes into the eye, as the image onto the retina, and then on the retina itself are a lot of photosensitive nerve cells that can detect changes in light, or with the cells along with the chemicals that exist on the retina can detect changes in light intensity and also kind of detect different wavelengths of light, and we interpret that signal in our brains to kind of form an image of the world. So we see light coming into our eyes, and then we detect the light, and our brains kind of interpret that into a useful information for us. So that's how we see. So only the light that comes into our eyes is available information for the brain. And so at the back of the eye, there's two kinds of photoreceptors. There's things called rods because they look like rods if you kind of put them in a microscope. The rods function effectively in low light conditions, but they cannot distinguish between different colors, which is to say, the rods can't distinguish between the different wavelengths of light. So it can detect intensities of light, but not wavelengths. So if you kind of just turn on the lights off and you're at night, you'll notice that the things you can kind of see things in the dark, even with very low light conditions, but you can't see colors. So things will appear to be kind of grayscale, or you don't see kind of very much color if it's very dark, because your rods are functioning at that time. Whereas the cones, they call that because they look like cones. The other type of photoreceptor are the cones, and there are 3 types of cones, and each type is sensitive to a different frequency of light. So there's kind of short cones, medium cones, and long cones. The short cones are most sensitive to this kind of purple color, and then the medium cone is most sensitive to green, and then the long cones are most sensitive to a yellowish kind of color. And because we have 3 kinds of cones, we see 3 primary colors. Now, if you just kind of measure light in a purely scientific sense, there's not colors, because it's only different frequencies of light. So the wavelengths are continuous, or either changes in wavelengths. There's no discrete red, green, and blue, or anything of the sort in the energy itself. It's because we have 3 types of cones that we see 3 colors, or we see kind of 3 primary colors that all the other colors are mixed together from. We don't actually, well, as we said here, we see purple, green, and yellow really, but once it goes into our brain actually kind of pulls those colors apart a little bit, and it gives us red, green, and blue. So the combination of the eye, the photoreceptors in the eye, and the brain processing the signal gives us 3 primary colors, which is red, green, and blue. And then all other colors are mixed together from that, which is basically to say, I hope I'm explaining this well enough, which is basically to say that different intensities from each type of cones in the eye mixed together gives us all the different colors that we see. Now the colors aren't actually there. It's basically just kind of 3 different wavelengths of light that we are sensitive to, but different mixtures of those 3 allow us to detect all the colors in between. That's what it means. Hopefully that makes sense. It probably doesn't. But anyway, so the effect of our eyes and the brain is that we see 3 primary colors. And when you kind of mix different colors lights together, if you mix all 3 lights, like red light and green light and blue light together, you get white light. Or alternatively, you can split light apart. If you put it in a prism, and kind of what comes out the other side is a rainbow that splits the white light into the different frequencies. Basically, the prism selectively refracts the different frequencies of light. Depending on different frequency, it refracts to a different direction, right? And so then you get a rainbow, because you get a continuous change in the spectrum of light as you kind of move from one position to the other, move from one angle to the other of the light coming out of the prism. Again, I'm not explaining it very well. I need more diagrams, I guess. But that's where rainbows come from, because of that refraction and the different angles of refraction depending on the frequency of the light. I'm pretty sure I'm not explaining this well enough, but so when you mix light together, you get this. But when you mix paints or pigments together, you get this. Now, why is that? Because if something appears to be red on a surface, like if you have a red pen or a red piece of paper, for example, the reason that it's red is because it's not reflecting the other colors. It's only reflecting red, but it's not reflecting green or blue. Whereas if a thing is yellow, for example, it reflects both red and green, but it doesn't reflect blue. Because the white light will hit the surface of the object, and certain frequencies will reflect back into your eye, and you see those, and you say that's the color of the object. Whereas other frequencies will be absorbed and not reflected, and the thing is not those colors. So because the color of the object is the reflection of the light, it means that when you make things a certain color, it's the opposite of light. So when you mix paints, it's the opposite of mixing lights, because when you mix paints, you're controlling what you absorb. Whereas when you mix lights, you're mixing together what light you see. Does that make that still doesn't make any sense unless you actually try. If you have any free time and you have paints, just go play with paints. That's probably the easiest way to do this. Just get a bunch of paints and just kind of mix them together and see what kind of weird colors you get. And just notice that it's difficult to explain in words, because this sort of stuff you just have to do it to try it out. So for subtractive colors is when you actually mix paints or pigments together, it becomes yellow, magenta, and cyan. So you mix magenta and cyan together to get blue. You mix magenta and yellow together to get red. You mix yellow and cyan together to get green, which is like the opposite of this. Whereas here, if you're mixing lights, you mix green light and blue light to get cyan light, or you mix green light and red light to get yellow light. So it's literally the exact opposite. Although with pigments, you also need black, because if you notice that magenta and yellow and cyan gives you this kind of grayish color, it's not really black. So in order to get black, you also need to add black, because paints are limited in the kinds of colors you can mix together. Whereas with lights, you just get all the colors. Hopefully that's clear enough. If you don't understand this, it doesn't really matter that much. If you do understand it, then you're more clever, and that's good for you. But if you really don't understand it, it's not that important. But it's always good to know the science, I think. So why do we see colors? Why do we see colors? Well, vision, or the ability to see, is more useful to us if we can quickly and efficiently understand our environment. So what you want out of a sense is that you can just kind of look out and see things and get useful information out of it. So if you look at a picture like this, for example, this is a picture of an orange tree. You notice that the oranges are bright yellow, the leaves are green, and the sky is blue. They're all different colors. So you're just looking at this, you can very quickly differentiate between the sky and the leaves and the oranges. And what you really want are the oranges, because that's food. So for somebody who needs food to survive, you just kind of look out into the environment, and immediately you can identify where the food is if you look at a picture like this. So that's useful. It's useful to be able to have these three different colors, and also know that the yellow stuff is the stuff we want. But also it's also useful to know that there's a tree there, and that you can differentiate from the sky, for instance, because you want to climb the tree and not get confused. Imagine if everything's the same color. Or imagine if the yellow and the green is the same color, then you can't see the oranges amongst the leaves. That's not useful. So, the reason we see colors like this is because it helps us understand the world. Like, it helps the brain process information more quickly if you can separate things into colors. And, just as an aside, it's also useful for the tree to make the oranges visible to us, because the tree uses animals to to propagate the seeds. Like when animals eat the oranges, they take the seeds somewhere else and they kind of throw it on the ground and they plant it on the ground. So it's actually like the tree also wants animals to see the fruit because it's this kind of symbiotic relationship between trees and animals that the animals kind of help like they eat the fruit and then they take the seeds somewhere else and plant it. So that's useful for the tree as well. Anyway, back to colors. So it's helpful because colors allow us to quickly understand the world. And if you color code things so that different things are different colors, then you can identify things easily and quickly. Now, over time and through human history, certain colors have become associated with certain concepts. Partly due to the way we observe colors in the natural world, but also partly due to cultural conventions that don't really have anything to do with what's really in the world, but has more to do with kind of history and conventions. So, this is kind of giant red heart here. The shape of it, it's a heart, even though it doesn't actually look anything like a heart. The heart that's in your body doesn't look like that. But it's also red, and in, I guess, Western civilizations, red is associated with love, but also with danger sometimes. Like if red alert is a dangerous kind of thing. So this really kind of strong color is associated with love and danger. And other colors like, yellow is associated with warmth and happiness, and green is associated with nature, and blue is associated with calmness and cold, and purple, interestingly, is associated with luxury and wealth. Which, if you don't know where that comes from, it's because back in the olden days, purple dye was made from the blood of a shellfish, and so and these shellfish are these tiny little things that don't have very much blood in them. So in order to make a piece of purple cloth, you had to kill a lot of shellfish, and that made the cloth really expensive, or it made the dye expensive, so it made the cloth expensive. So the Roman emperors wore purple clothing because that was like the most expensive clothing you could buy with money back then. So purple has become associated with wealth because purple dye was expensive, not because there's anything inherently expensive about purple, but just the fact that the dye was expensive back then. It's not expensive anymore because we use chemical dyes these days and synthetic colors, and it's not expensive. But it retains that association, right? And then when you kind of think about colors and their cultural associations, it's very important to also keep in mind that there are cultural differences between different parts of the world. For example, in China, red is associated with happiness and with prosperity, which is completely different, from the Western tradition. Like, prosperity is not red and also in China and also in other Asian countries, white is associated with death. So if you're doing white business, or you're dealing with white matters, it basically is like a euphemism for dealing with death and funerals. Whereas in Western culture, black is associated with funerals, and black is death. So it's like the complete opposite. Like on one side of the world, white is death. On the other side of the world, black is death. So some of these colors are, and the meanings associated with these colors are completely dependent on the culture, which is a bit strange. Although, green is always going to be nature because that's the color of leaves everywhere in the world. So, nobody confuses green for death, which is kind of, that would be weird, right? So some things that are based on actual observations of nature would remain consistent between cultures, but other colors are just completely arbitrary, it seems. And you just have to kind of be aware of these things depending on where you're designing. And it's also unavoidable too, because these kind of associations of colors are so common that if you use a color, then once people see the color, they think of the association, and you can't really stop that from happening. So you kind of have to respect it. So this here is the red, yellow, blue color wheel. I'm putting it here because it's very common. The red, yellow, blue color scheme, it predates our modern scientific understanding of colors. So it came from a time when we didn't really understand, wavelengths and electromagnetic radiation. Like, this was because artists kind of mixing paints together. And it's still commonly taught to art students and sometimes to architects, but it's actually not scientifically accurate. The reason they had this particular scheme, red, blue, and yellow, is because the way the paints work, and like paint is basically pigments, and pigments is basically fragments of colorful material in the medium. So, iron oxide is reddish brown, right? So you kind of get iron oxide powder and you mix it with stuff like egg whites or something, and then you kind of put it on the surface. The egg white dries and it sticks the iron oxide onto the surface. That's basically paints. Like it's kind of little bits of color in a medium that will stick to a surface. So that's how paints work. But old school paints, where you're kind of mixing these minerals and other materials together to get these colors. When you get a very low saturation red, so you kind of take red and you thin it out, it appears magenta. So when it's kind of thick paint, the paint looks like red, but when you thin it out, it looks magenta because the way the material worked, the hue or the light frequency that's reflected actually changes depending on how thick it is. And the same with blue. Like a thick blue is a dark blue, but the thin blue becomes cyan. So it's because the paints themselves did not have a consistent appearance depending on their thickness. That's why people thought that the primary colors were red, yellow, and blue, when actually the primary colors were red, cyan, and magenta because the red became magenta when you thinned it out, and the blue became cyan when you thinned it out. So really it's supposed to be red, yellow, and cyan. I mean, magenta's yellow and cyan. But they thought it was red, yellow, and blue, and then people continue to teach red, yellow, and blue in art schools. And even today, like a lot of paints still work like that. When you kind of get thin red paint, it becomes magenta. But the problem is if you use a computer, it doesn't do that. Like a pale red is just pink, it's just pale red. And a pale blue is just pale blue, and a pale green is just pale green. So when you use kind of a computer to define colors, then the colors don't shift hues. Whereas if you use paints, they do shift hues. So this red, yellow, and blue stuff, you might see a lot in art books, or if you kind of take art lessons, they might teach you this stuff. Just keep in mind that it's not the same as the kind of colors you see on computers, for example, and it's also not quite the same as what scientists understand as colors and light frequencies. Just something to keep in mind. Alright, so that's all the science and all the theory and all the kind of ideas. Let's look at architecture. So one of the most common misconceptions in architecture is that the classical Greek temples were white. If you look at the ruins of kind of old Greek temples, like the Pantheon and other temples, you often see these kind of white stone buildings. And because there's so many kind of beautiful white stone buildings that remain from ancient Greek and ancient Roman architecture, what people have subsequently done is build similarly majestic white buildings, like the Jefferson Memorial here. Like it's built in America, it's not Greek, but it's it's using that Greek style and it's using the white stone. The problem is that for a long time people didn't realize that the Greek buildings, well, actually they did realize, they just didn't bother kind of talking about it. Like the Greeks actually painted their temples in bright colors. And at the bottom here, you see this kind of red and blue and white, of course. I mean, the temple is mostly white, but they kind of had these kind of bright colors, bright red and bright blue paints on the temple. So the temples were never completely white. But the problem with the Greek ruins was that while the stone lasts several thousand years and they're still standing today, some of them, the paint doesn't last very long. Paint technology back then was very poor, and so the paint didn't last very long at all. I think they had to kind of repaint the temples every year or so because the paint didn't last very long. So all the paint has washed off these ruins, but the white stone remains. And then when architects look at these white ruins, they thought, wow, what a beautiful white building. And then they go around building other white buildings when the original Greeks didn't really intend for these to be white. They intended for these things to be painted the whole time. So that's kind of funny. There's kind of interesting misunderstanding in architecture, and people have known this for a long time. And then even today, if people like, if they would take kind of microscopic paint fragments from the stone, and they would kind of figure out what colors these were, but you can't see them anymore because most of it has washed off. So so yeah, like if you see a majestic white building somewhere, now you know that it's actually a really interesting misunderstanding of what the Greeks really intended. But there you go, colors. Another example, and this is not the best photo of it, to be honest. It's the city of Petra, also known as the Rose City. It's carved into a valley in Jordan, and the valley has this really interesting pink color in the stone. But the problem with this photo is that I think the camera might have done some color adjustment, or maybe it was just taken on midday or something. A lot of the time, it's a much more pink than this, especially like in the evenings when the sun is lower in the sky. But the whole valley is this beautiful pink color, and this city is just carved into the cliffs of this valley, and it's amazing, this place. I've never been there myself. I probably should at some point. But anyway, it's incredible, and it's mostly due to the fact that the ground is pink. It's not because the people there decided to make the buildings pink, but it's because the stone itself is the beautiful color. So it's quite a remarkable ruin. The architecture is interesting too, like it's all carved into the cliff. It's not, most buildings are built out of stone, whereas this is carved into stone, which is like the opposite, right? Very interesting city. Another example of famous colors, this is the city of Siena in Italy, which, like the name, has become synonymous with the color sienna, which is a range of these browns. And the reason that everything in the city is this interesting brown color is because there's a lot of iron oxide and manganese oxide in the local clay. And so when you make bricks out of this clay, it comes out as this beautiful brown color and all these kind of interesting brown tones everywhere. And so all the buildings in the city are these interesting brown shades because of the iron oxide and the manganese oxide in the soil that they make the bricks out of, and which is interesting. Yeah, I mean, Siena. That's what the color is called. Like the city is called Siena, and the color is called Siena, except it's got two N's instead of one. So, the color has become so famous that it's been named after the city. I also think this is not the best photo to demonstrate this. The problem with photographs, and maybe it's my computer screen too, like when you take a photograph, the photo doesn't really capture the true colors because there's limitations in the camera and the film, or the digital sensor on your digital camera if you don't use film anymore. Nobody uses film anymore. And also, when you kind of put it on a computer screen, your computer screen is also probably not showing all the colors completely. If you want to do some research, you can look this up. Most computer screens can only show a limited set of colors, and so if you look at things on the computer screen, there's literally colors that it cannot show. It will approximate it with the nearest color, but there's actually a lot of colors that most screens and most television screens can't show you. And if you print it out on a printer, the printer can't print all the colors neither. So anything that's been reproduced usually is unable to create the full range of colors that you would see in real life. So I guess what I'm trying to say is, go to Petra and see it with your own eyes, and go to Siena and just see it with your own eyes. It looks better in real life. Unless maybe if you're colorblind, in which case that's kind of unfortunate. A third example, or is it the fourth? This is the interior of the Barcelona pavilion, designed by Ludwig Mies van der Rohe. Mies van der Rohe is his last name. Ludwig is his first name. So the Barcelona pavilion was built in Barcelona, and it's rather famous as a piece of early modern architecture, and also famous for the rather expensive materials that were used in it. So there's green marble, there's red onyx. So the green marble you see, like in the picture, you see the back wall to the right, that's green marble. The red onyx is to the left, to the front. That wall is green as a red onyx. The white travertine is the white stone on the ground. And then there's also tinted glass and a reflective water pool. So this building is a pavilion. It's not very big, but it uses these really expensive stones, and it looks pretty good. But it was really expensive to make because it uses all these rare stones, right? So that's kind of fancy. That's pretty cool if you want to use rare stones in your architecture, even though you might find it to be very expensive. Luxury stones, man. And here's the Guggenheim Museum in Bilbao. I think we've seen this in an earlier lecture, but the silver color of it is because of the titanium sheeting that they used to cover the entire building. Titanium sheets to cover the entire building. Now, normally titanium is quite expensive, and you can't actually afford to build buildings out of titanium because it's expensive. But interestingly, right around the time when this building was built, a large quantity of Russian surplus titanium was put on the market. Like, this was kind of around the time when the Soviet Union, or it was afterwards. It was after the Soviet Union collapsed, and the Russians had a lot of titanium, and they were preparing to use it to build things like military aircraft, right? But after a while, they decided, well, we're not going to build that many military aircraft anymore, and we need money right now. So they sold the titanium for cheap, and these guys bought a lot of it, and they just put it on the building. So at any other time in history, you wouldn't be able to afford all this titanium to put on the building, which is kind of ridiculous. Like, you want to build planes with it or something, right? But they bought it for cheap, and then they kind of covered the building with it. So that made it affordable. Otherwise, it wouldn't have been affordable. So that was an interesting story. So what happens here is that then you have this kind of interesting building that's completely covered with this reflective material, and it's all different shapes, right? And so as the sun kind of hits it at certain angles, then different parts of it are highlighted, and then other parts are shadowed. And so as the sun moves across the sky, there's always this constantly changing pattern of light and shadow and reflections on the building itself, and so it looks like it's always kind of different. In different times of the day you look at it, it looks different every time. So that's kind of interesting. This is the Horyuji Pagoda in Japan. This is one of the world's oldest timber buildings, if not the oldest timber building in the world. Timber is a very common architecture materials, but timber unfortunately doesn't last very long. So this building was from the 600 AD, so around about, what is that, 1,400 years ago? Is that about it? Around about 1,400 years ago. So this is like the oldest, one of the oldest, if not the oldest timber structure in the world, because timber doesn't last all that long usually. It can rot, it can burn down. So I mean, compared to stone, it's not as sturdy, right? It's not as long lasting. But timber gives you these interesting brown hues, and then a lot of people like timber because of the warm brown tones, like because it's kind of brown and yellow, so that it's a warm color, and there's a lot of people like that. So, but unfortunately, there's not that many examples of kind of old timber buildings, the way we kind of find old stone buildings like these Greek temples everywhere. But some notable examples like the Horyuji Pagoda remains, or Horyuji, that. And as you can see, there's this kind of rich brown color, which is also interesting, almost like the sienna color from Sienna, except that's clay, and whereas this is wood. This is the Dome of the Rock in Jerusalem, and well, I mean, you can see in the picture there's gold on the dome. That is literally gold. Literally gold, added in 1993. So before that, it was an interesting aluminium bronze alloy, which was also a yellowish color, but not quite as bright. And then before that, it was lead. So the gold was added recently, but the tiles on the border is also interesting. So there's kind of these really intricate blue porcelain tiles, or blue, green, and yellow porcelain tiles around the edge as well. I mean, if you look at it, it kind of looks like a rising sun above the sky, right? Because of the kind of golden globe above the blue foundation or the blue base. So it looks kind of like the sun on the sky. So it's pretty striking building, especially since they put real gold on the dome. That's pretty amazing. So again, yeah, use of colors. You really kind of striking use of colors. Gold again is usually not that affordable to be put on buildings, but occasionally, especially for significant religious buildings, people decide that hey, it's important enough for us to spend this money, so they spend the money. I think it was the King of Jordan who donated the gold for the dome. And this is the interior of St. Mark's Basilica in Venice. Again, a lot of gold. This time, gold glass mosaics, which is gold leaf inside glass tiles. And then the glass, so it's a glass tile, but there's kind of gold leaf in it, so it looks like gold. And then you kind of use the tiles to build these mosaics on the ceiling and the columns in St. Mark's Basilica in Venice. Again, a lot of gold, but also a lot of kind of other decorations too. You have mosaics of Jesus and saints and other notable biblical characters, right? So again, a lot of gold covering the interior of an important religious building. Gold glass, it's not... The thing about the gold glass is like Venice also had a quite notable glass industry as well. So it's a kind of a technology that was, I mean, it wasn't unique to Venice, but they certainly had quite a robust glass industry, and so they could make these gold glass tiles because they had the expertise to do so, and they covered the inside of their basilica with it because it looks good. All right, let's move on. So for the fourth exercise, you're going to work on the residences. So you see the circle there. What you are given is 2 apartment buildings built in dirt. So it's a dirt house in Minecraft. And your job is to replace all of the dirt with either colored wool or colored clay. Now, whichever material you choose, either the wool or the clay, you must use every color of that series. So there's 16 different colors of wool and 16 different colors of clay. You need to use every single one of those colors somewhere on these 2 dirt buildings. And the idea is to try to make it look good, not look like a giant mess of different colors, obviously. So try to use colors cleverly, and as you kind of try to think about what colors to use where, consider the different meanings of colors. If blue is calm and cool, maybe you want that in a bedroom because it's calm. Or maybe you want red because you want interesting things to happen in a bedroom. I don't know. Maybe you want a neutral color in the lounge, or maybe you want kind of a more intense and interesting color. I don't know. You have to decide where you want things. So also just consider that often less is more. If you just kind of put all 16 different colors next to each other, that might be a bit too much. Too many colors in the same space can look a bit messy. So change all the dirt into the colors and see how you go. So basically the point of this exercise is to experiment with colors, and through the experimentation figure out what you like and what you don't like, and what looks good and what doesn't look good. Alright, those are the image licenses for copyright purposes, and in the next video I will have a go at this. I'll be honest, I'm not, color is not my most proficient thing, but I'll give it a go. If you notice the exercises so far is that we kind of go through these concepts, and you have to try out each one different, in the different exercises. And the whole point is to make sure you try all the different things. So if you feel like you're not good at one thing, don't hide from it. Just learn about it and get better at it. So I'm personally not the best person to deal with color, but I'll have a go because it's important to get better at things. I'll see you guys in the next video.